Science IRL round 1. So this time we are doing matter with marshmallows. So what do you need? You need a bag of jet puffed. Not really. You just need some colorful marshmallows. Now, these are the citrus variety. Yum. Not really. We have yet to decide why anybody would want the citrus variety. So I'm just going to assume they made these for us, for science. So you need some of these. If you can't find these though, just take the white marshmallows, get some markers or Sharpies, and put a dot of different colors on different ones. So problem solving. So marshmallows, you're gonna sort them out into the colors. Whoops, run away. Oh no, he really doesn't want to be in there. Okay, so I've got green, I've got yellow, and I've got pink. So my pink are actually gonna be my oxygen atoms, just like in the matter video with Legos. My green are my carbon atoms, just like the matter video, and yellow are hydrogen. So I've got my 3 different elements, a bunch of atoms, or marshmallows. I've got my bonds, my chemical bonds, which are toothpicks. Get the kind with the pointy ends. It'll make your life easier. Whoops. And then I've also got some background decor. These are my plant children. This is Ruth. We can see that she has some green on her. So she's probably doing some photosynthesis. That's why she stays in the windowsill. And then this is Pip the Pumpkin. And Pip doesn't do any photosynthesis. Pip is actually a fruit. That's why he's got seeds on the inside. But his plant that he was harvested off of, that was a sad day. But his plant, it did photosynthesis. So Pip is a storage device for sugars. That's cool. And Pip stays in the window just to keep Ruth company, but he doesn't really need sunlight. Anyway, and then you need a fresh slice of paper, straight from the tree. That's sad. And then you need a Sharpie. So what's the slice of paper for? It's for the photosynthesis equation. So we're going to explore matter by talking about Breathe. Okay, so photosynthesis, here's the equation. I need 6 molecules of carbon dioxide. I need 6 molecules of water. And then with a little bit of light from the sun, I can make glucose, C6H12O6, and 6 molecules of oxygen gas. All right, so let's just look at this, break this down a little. My big numbers in front of each molecule, those say how many of the whole molecule I have. So I have 6 molecules of water, H2O. But the little numbers after a letter, an atom, that means that I have 2 atoms of oxygen in this carbon dioxide molecule. So fun math question, how many molecules, how many atoms of oxygen do I have in all 6 molecules of carbon dioxide? Think, pause, wonder, ponder. I'm actually gonna multiply that 6 by 2, and there's 12 atoms of oxygen in these 6 molecules. So quiz yourself on the rest of these, or not, that's not super fun. And then let's build. So what I want you to do in the first part of this lab is try building every molecule in your photosynthesis equation. So to get started, I'm gonna work on this CO2 molecule. So I'm gonna need my carbon, my green marshmallow mountain here, and I'm gonna need my oxygen. So let's get building. These, I left them out for a while, so they're a little stale. So it's prime building material, guys. So I've got a carbon, I'm gonna attach that to an oxygen, and then I'm gonna attach the same carbon to another oxygen. Boom, CO2. Now, I need to build my water molecule. So I need, this time, not carbon, but oxygen and hydrogen. So I'm going to take my oxygen and attach it to a hydrogen. And I'm going to take this oxygen, and I'm going to attach it to another hydrogen. And there's my H2O. If you really want, make 6 of each. So my light, it's not a molecule, so I've got no work to do there. I guess I could get a lamp and shine it on these things, but I don't think much would happen, except maybe some melting. So I'm going to skip this guy because glucose is kind of a big one. This is our glucose. So I'm going to move right on to oxygen gas. And oxygen gas only has 2 atoms, but if you're interested in chemistry, you might like to know that these 2 atoms are held together by a double bond. So if you really want, you can take 2 toothpicks and bond your oxygens together like that. That would be the most accurate way to build an oxygen molecule. So there's my double bonded oxygen. And now I'm going to tackle this glucose thing. Alright, so I've built my glucose molecule now. Come take a look at it with me. Like I said, my carbons, my green atoms, are here in a zigzag. A funky thing you'll notice is that one of my carbons is attached to 2 hydrogens, okay, and one of them is attached to its oxygen with a double bond, 2 toothpicks. Why, you might ask? Take chemistry, it'll be great. But so here's my photosynthesis equation. I've got carbon dioxide and water as my ingredients or reactants. These are the things I need for photosynthesis. I also need light, so I'm gonna make it include that too. And then these here, glucose and oxygen, are my products. So I've got my double bonded oxygen gas molecule and my mega glucose molecule. Hi, bonus round. We're gonna do some physics now, because why not? And I have this whole bag of orange marshmallows that I didn't want before. So this is the physics version. Here's what you need. You need a plate, preferably one that you don't care a lot about. So like the one your sister painted at the Paint Your Own Pottery, let's leave that alone. So something you don't care too much about that's microwave safe. You need a fresh slice of physics paper. You need a ruler. See, this is my one with the dancing mooses on it. It's pretty great. And yeah, you need some orange marshmallows and a fantastic attitude. And so let's take a trip over to my microwave. I'm gonna make a quick amendment here, and I'm gonna take the turntable out. Why, you might ask? So microwaves basically work because they have wavelengths. Yep, light goes like that. They have wavelengths that are the right length to heat up your food. Things like water and fats and carbs, these are the right wavelength for that. But what happens is because of this thing called interference in your microwave, there's hot spots and there's cold spots. So this guy rotates your food around and makes sure that it doesn't just stay in a cold spot or a hot spot. But I'm gonna take it out because I don't want my hot spots. So I'm gonna insert my plate like so. Just let it rest peacefully right there. And then I'm gonna close this up and I'm gonna do some cooking. How long, you might ask? I don't know, until I'm ready. So you might wanna experiment with some different times, but I'm just gonna wait until I see things starting to happen. It's gonna puff up a little bit in some places, not others. Let's see what happens. I'm gonna cook it a little more. Guys, this is how I do microwaving in real life too. I don't know about the instructions. Oh, that happened. Something happened there. Okay, so look at this. Look at this. Really close. Okay, so these guys unaffected, but there's hot spots right here. So what I want to do is make a note that that was a hot spot and that was a hot spot, and now I want to measure that. So let's take my moose ruler. I'm going to use centimeters because centimeters are for science, and I'm going to measure a spot like here-ish and here-ish. Oops, did that work? I don't know, whatever. All right, so I got from here to there, would you say like probably about 6 centimeters? Okay, so I'm gonna write that down, get the marshmallow off my mooses, and I'm done with those things. So here's the equation I need today, okay? So what we're gonna figure out is the speed of the waves that are heating my food. What? Okay. So there's an equation I need, and that equation is wavelength times frequency, and that's going to give me the speed of the waves heating my food. Watch this. Okay, so what did we just measure? We measured our wavelength. So I'm going to write 6 centimeters right there. That's my wavelength. What's a wavelength, you might ask? Well, let's look at some nice waves. So this is literally what the energy heating your microwave looks like, or heating your food looks like from your microwave. Now the distance between the peaks of waves, that's the wavelength. So for our microwave, 6 centimeters. Frequency, we're gonna have to go back to the microwave. Come with me. All right, so let's zoom in here. And my microwave says that I've got 1,000 watts. Okay, so now it's time to Google. I need to Google, what is the frequency of a 1,000-watt microwave? Guys, if you ever have a question, ask Google. Don't go like, I don't know how to figure that out. So I Googled this, and I had to like click on a couple websites, but here's what I came up with. I came up with 2,450 big M, big H, little z. What the heck does that mean? It's megahertz. So mega means I need to multiply by 1 million. That's mega. Now hertz are this unit in physics that mean per second. Now that's a weird one because the unit is actually like something per second. Okay, so that's hertz. Mega means times a million. So what I'm going to do is I'm going to change this into 2450, and then I'm going to add 6 zeros to take care of my mega. That's my million. So it's going to be 2,450,000,000 per second. Okay. Now I need a calculator that can do these zeros. So I phoned a friend because my iPhone didn't want to. So I'm going to multiply 2,450,000,000 per second times my 6 centimeters. But if I want to figure out the speed of the waves, I'm going to end up with something that's in meters per second. So I'm just going to turn this into meters really quick. And I missed a step because I need to multiply my 6 centimeters times 2 in order to get my entire wavelength. So this is going to end up being 12 centimeters, which is equal to 0.12 meters, okay? So my wavelength is 0.12 meters. Now, if you're confused about why I multiplied by 2, my 6 centimeters was this distance. This was 6 centimeters. So in order to get my whole wavelength, that would be 12 centimeters. Now I turn that into meters. I've got my 2,450,000,000 per second as my frequency. And now I'm about to find the speed of the waves in my microwave. So calculator at the ready. 2, 4, 5, 0, 0, 0, 0, 0, 0, 0 times 0.12 equals 294,000,000 meters per second. Now, what does that mean? Is it cool? I don't know. Let's see how close we got to the speed of light. So I'm going to look up, like I said, when in doubt, Google it. So the speed of light, look at that, y'all. Look how close we are. Speed of light is 299,792,458 meters per second. That's pretty darn close if you ask me. So, congratulations. You have just measured the speed of light with marshmallows, a moose ruler, and your microwave. Now, before you're done, put it back together so that I don't get in trouble. See you later.